Today, we're going to discuss confidence intervals for a sample proportion. What you should already know is how to apply the four-step process for constructing and sketching a confidence interval for a sample proportion. In today's video, we're going to cover two things. First, we will discuss the motivation behind using confidence intervals as a means of estimating a population proportion. And then secondly, we're going to discuss the one aspect of constructing a confidence interval that was not covered in the section 5.2 preview, namely how to find z asterisk. So let's start by taking a look at the motivation behind using confidence intervals as a means of estimating a population proportion. Here's an example of a question I might want to answer. What was the proportion of U.S. voters that voted for a particular presidential candidate in the last election? Well, as a way of starting to take a look at how we could illustrate conceptually a way of finding an answer to that question, let's start by drawing a line on our screen. We'll call that the p-hat or sample proportion axis. We know that the range of values that we could possibly be interested in go between 0 and 1. In other words, 0 represents 0% of voters voting for that presidential candidate. 1 represents 100% of all voters voting for that presidential candidate. And somewhere in between, in that range of values between 0 and 1, is going to lie our true population proportion of voters. We'll call that P, standing for population proportion. Now, how do we get at this value? How do we start to try and find an estimate for that population proportion? Because we're not going to go out and actually check with every single U.S. voter to see if they voted for the candidate or not. That would be too difficult to do. So what we're going to do is we're going to gather a random sample of voters, and we're going to find the proportion of them that voted for that candidate. And that is shown on the screen as a small triangle. And I have labeled that p-hat subscript 0. And that's what we call our point estimate. And again, we derived that from a single sample of data. Now, notice that there's a difference between that triangle and that half circle. That difference is known as the sampling error. In other words, there's a certain amount of error associated with my point estimate. It doesn't lie on top of the population proportion value. And if I were to gather another sample, and I were to find the sample proportion of that sample of voters that voted for the candidate, I would probably get a different error. So the question now comes up, if we've got this error associated with a sample, is there a way that we can somehow take that error into account? And the answer is yes. What we're going to do is this. On the screen, notice I've added some parentheses, a left and a right parenthesis that are equidistant. They're the same distance away from the triangle, our point estimate, p-hat subscript 0. We call this distance from the triangle to these parentheses the margin of error. And notice that within this range of values that I now have bounded by this parentheses, I'm going to shade that. Now notice that that interval contains the population proportion. So what I've kind of done is thrown out this net with the represented by the parentheses to create a range of values that we call a confidence interval. And our hope is that the confidence interval would contain within it the population proportion. Now, how do we construct that particular interval? Well, we do so by having what's called the margin of error as the distance below and the distance above our point estimate, p-hat subscript 0, to create this interval, this confidence interval of possible values that we hope will contain the true population proportion. All right, and then we would label the left side of this interval p-hat subscript 1 and the right-hand side p-hat subscript 2, and that would define the endpoints for our interval. Now again, notice that the interval of values that we constructed around p-hat subscript 0 is known as a confidence interval because the size of the interval is based on how confident we want to be in capturing the true population proportion parameter, which is in this case p. So we have to have given to us some sort of confidence level that we want to construct that interval with, say 95% confident, or if we want to be 99% confident, whatever. That's how we're going to express our confidence. Now, using the notation that was introduced in the sketch, we can write our confidence interval in one of two ways, either using interval notation, where we have parentheses with the endpoints designating the range of values for that interval. And again, P1 hat is equal to P hat subscript 0 minus the margin of error, and then we add the margin of error to P hat subscript 0 to get the other right-hand side endpoint. And then another way of writing that interval is as P hat subscript 0 plus and minus the margin of error. Now, note that in the confidence interval that I've shown, the only unknown quantity that we had to introduce to create the interval was the margin of error. We already knew the sample proportion value, that was our point estimate, and based on the confidence level, that gave us how large we want our margin of error to be. So if I have a large level of confidence or confidence level, then I'll have a large margin of error. If I have a small confidence level, I'll have a smaller margin of error. So having said that, from our textbook and the preview for section 5.2, we saw that the margin of error is nothing more than the number of standard errors distance above and below the sample proportion value based on the confidence level. In fact, the formula is given on the screen. It's Z asterisk, where Z asterisk depends on the confidence level, and I'll talk about that in a minute, times the size of the standard error. Note that the only unknown quantity in this formula is the Z asterisk value, because we already have another formula for the standard error. So intuitively, as I've already mentioned, it should make sense that the higher the confidence level we want, the larger the margin of error should be as a result, so that we're more likely to capture the true population proportion P. In fact, from section 5.2.3 of our textbook, we discovered that the way that we can connect a confidence level with the margin of error is through the mechanism of z-scores associated with a standard normal distribution, namely the Z asterisk value. And that's going to lead us to the second part of our discussion for today. So now that we've seen conceptually that the only thing we really don't know in the margin of error formula is Z asterisk, the question comes up, how do we go about finding the Z asterisk value that we're going to need for constructing our confidence interval? So here's how we're going to do it. Notice that the confidence level is going to correspond to a region on the standard normal distribution curve that is right smack in the middle. So we're going to select Z asterisk so that the area between negative Z asterisk and Z asterisk in that standard normal distribution corresponds to that area in the middle, which is the confidence level. And notice also that what that means is that the right tail area will be 1 minus the confidence level. That gives us the area in both tails divided by 2, because then that gives us the area in either of the tails, the left or the right, for that particular standard normal distribution. So knowing that, to find Z asterisk then for a particular confidence level, we would simply use our guru's continuous distributions probability calculator, the probability to value function, with a standard normal distribution and upper tail area equal to 1 minus the confidence level, all divided by 2. So let's look at an example of how we would go about doing that, finding Z asterisk for an 80% confidence level. So the first thing we start by doing is calculating the upper tail area for that confidence level. Notice that an 80% confidence level would correspond to an upper tail area of 1 minus 8/10, all divided by 2, which equals a value of 1/10. Now, let's go to our guru and see what z-score value, Z asterisk value, would then correspond to that right tail area. All right, so here we are in the RGuru Continuous Distributions Probability Calculator. I have selected the probability to values radio button, distributions normal, standard normal distribution, so the mean is 0, standard deviation 1. I'm looking for the value, the z-score value, when the upper tail area corresponds to 0.1, 1/10. And so I go ahead and hit preview, and I see that my z-score value to 2 decimal places, because we always round this to 2 decimal places, is approximately 1 28/100. So to conclude our example, now that we've used our guru's continuous distributions probability calculator, probability to values function, we saw from that in this case, for an 80% confidence level, we get that Z asterisk is approximately 1 in 2800ths. Let's go ahead and summarize what we've looked at in this particular video. We began by showing, conceptually, the motivation behind using confidence intervals as opposed to just a point estimate as a means of estimating a population proportion. The only two quantities that are needed for constructing such a confidence interval are the sample proportion value and a confidence level. We saw, secondly, that to find the margin of error for a given confidence level, we use the confidence level and our guru to find a corresponding z asterisk value. Then our margin of error is simply z asterisk times the standard error in that case. And then we can also use all of that information to draw a sketch of our confidence interval. And that concludes this presentation.